Welcome to Unit 6, first lecture, Chem 1111. It's all about bonding in this chapter. And I'm going to start by actually something that's not in this chapter, but just to give us some context. So I'm going to go to my friend on Paint here and talk about ionic bonding, because the rest of the chapter is about covalent. But let me just remind you about ionic bonding. So ionic bonding is an electrostatic attraction between a cation and an anion. A metal transfers an electron, or more than one electron. Metal transfers electrons to nonmetals. And ionic bonding, when you name them, you don't use the prefixes like mono, di, tri. You don't do that for ionic. You will for covalent, but not for ionic. And so, for example, if I have sodium, here's 1 electron. There's fluorine with 7. So sodium wants to throw its electron over. I sometimes call these football diagrams. And it gets sodium plus, and then the fluoride minus. And that is the Lewis diagram, or the Lewis electron dot diagram, or the Lewis structure for the ionic compound sodium fluoride. Not everyone puts in the comma, I like to put it in. And the empirical formula, the simplest whole number ratio of cation to anion in the crystal lattice would be NaF. So that's an example of an ionic bond. The electrostatic force of attraction creates the bond. And we looked a bit at using Coulomb's law, KQ1, Q2 over R, to help us look at the strengths of bonds, right? Sodium fluoride would be a stronger bond than sodium chloride. It would have a stronger absolute value of lattice energy. Of course, I can do more than 1 electron. Here's calcium. It's got 2 electrons. There's oxygen with 6. So calcium oxide, both electrons are transferred over. So you get calcium 2 plus and then O2 minus. Notice that the octet rule is satisfied for the anion, and you draw all 8 electrons around it. We will see later that there are exceptions to the octet rule, but for now that's good. And the empirical formula would be CaO. Okay, so you can have hydrogen accepting electrons, and we can also use our crossover rule. You don't always have to put in those football diagrams. So here's calcium hydride. That's an ionic compound, and that's the empirical formula. CaH2, the Lewis diagram would be Ca2 plus H minus. So if you want more ionic bonding examples, or a lecture that I do on ionic bonding, I can certainly give it to you, because I've captured that on a screen capture program for my grade 12 students, and I can certainly, in fact, you don't even have to ask. I'll just email it to you, and you can look at the ionic bonding in more detail if you want. But the rest of the class is going to be on covalent bonding, the rest of this chapter. So let's go straight to our textbook here, and there we go. So let's look at the example of sharing of electrons. Sharing of electrons is what we call a covalent bond. Covalent bond. Oh, I highlighted it. That's fancy, eh? So covalent bonds are between nonmetals and other nonmetals. You can share 2, 4, even 6 electrons between the participating nuclei, and that business of attraction of one set of protons in a nuclei for the shared electrons balances with the attraction of the other nuclei for the shared electrons, fights with the repulsion between the nuclei, and you get a compromise and hopefully get a covalent bond if that's what you want. So the attractive energy between nuclei and electrons exceeds the repulsive energy arising from nuclear-nuclear and electron-electron interactions. That would give you a covalent bond. So it's best to see it in terms of an example. So I'm going to show you a picture right here on page 256 of what happens. So here's the simplest kind of neutral molecule, the hydrogen molecule, H2. I drew the little dash there. You remember that dash from last year. that dash refers to 2 electrons. So I can look at the interaction energy here versus this line here, which I can call internuclear separation, as it's called over here. So up here we're going to have repulsion dominating, and we're going to start to get destabilized, and here we will have attraction dominating below 0, and that'll lead us to forming a bond. Okay, so far away from each other, like infinitely far away from each other, one hydrogen atom doesn't even know the other hydrogen atom exists. Then as the 2 nuclei get closer to each other, you get electrons attracted to both nuclei, and the electron-nuclear attraction starts to dominate. So you start getting this well of stability. At the maximum stability, you're at what's called the equilibrium bond length. The equilibrium bond length, 74 picometers in this example. So at the bottom of the well, you have the maximum stability. You have the greatest preference of attraction over repulsion. Now, if you start to push the atoms too close together, then the repulsion between the positive charges and the repulsion between the negative charges with other negative charges wins out, and you start zooming up here, and your repulsion dominates. So within this well here, and of course the atoms vibrate around that bond, but within this well region, you're going to get covalent bond formation. If I look up a bit here, we see what's happening. If we have 2 atoms, here we have, let's say, here's hydrogen A and here's hydrogen B. So you have the proton of hydrogen A and the proton of hydrogen B repel each other. The electron of hydrogen A and the electron of hydrogen B repel each other. But the proton in hydrogen B attracts the electron in hydrogen A, and the proton in hydrogen A attracts the electron in hydrogen B. So you get this battle, competition, compromise to get you to the formation of covalent bond. And if I was looking at a fluorine-fluorine molecule, my well, I'd have a well too, but it would be slightly different shape because we got more protons involved, more electrons involved, and in fact I think it'll be lower down. Let's see, do I have a picture of that? I think I do. Bond length of molecular fluorine is 142, bond energy is 155. So if I'm looking here, let's go straight to the picture, I see that the blue one is the hydrogen. Oh, okay, and it turns out that the fluorine said it was lower, but no, it's higher up. So the well is shallower in the fluorine than it is in the hydrogen. Okay, I won't make too much of a fuss about these graphs, but I did want you to get the general idea that different graphs are going to have slightly different shapes, but you still got that well. If you don't have the well portion in there, if you don't have this well portion in there, then you cannot form a covalent bond. Okay? So let's go down here. Here we have, we say bond formation in hydrogen. Where are we looking at here? On page 257. Bond formation in hydrogen is easy to describe because we just place 2 electrons. But in other molecules, we have lots more electrons, of fates of which to figure out. Complex task, but one simplified way to describe many bonds requires the sharing of only 2 electrons. And what you do is you overlap the orbitals. This is one bonding method. We're going to get into more of this over this next, actually chapter 6 and 7 could be thought of as a super chapter because there's lots of overlap. That's a little joke for you. Overlap between those 2 chapters. So we can take a 2p orbital with just 1 electron in them on one fluorine. I can call this fluorine A, and then a 2p orbital on another atom, B, and I can overlap them together. And that overlap of orbitals, that creates a covalent bond. Okay. Now, what we drew there so far is hydrogen, fluorine. Those are examples of equal sharing of the valence electrons when we form the bond. When you have equal sharing, you say that the bond is non-polar. Some books just call it pure covalent. I like to call it non-polar covalent. It means there isn't a positive and a negative end to the bond. We say that the bond dipole, mu, the little vector arrow on it, is 0 if we have equal sharing. See, the positive and negative ends of the molecule coincide if we're talking about a molecule. But in terms of a bond, we say that the bond dipole is 0. Yes, I know we use mu for micro and a bunch of other things, but it is used for a bond dipole, and there is no die to it. There isn't a positive and a negative part because the sharing is equal. So whenever you have two atoms that are the same atom symbol, then your bond is nonpolar. So if I look at nitrogen, yeah, I know it's a triple bond. You remember that. That is a nonpolar bond. Oxygen, double bond. That is a nonpolar bond. Chlorine, single bond. That is a nonpolar bond. The stuff I'm putting around these atoms, these little dots, those are lone pairs. The dots, well, two dots makes a dash in the center, those are shared electrons or bond pairs. And we'll get into all that as we talk about Lewis diagrams. So just like if I have a Kit Kat and I'm sharing it with you, I would say, okay, here's two pieces, and I take two pieces because I'm a nice guy, so we would share them equally. But maybe I really want to be a super nice guy, and you'd say, hey, can we share? And I'd say, sure. And I give you three pieces and just keep one for myself. Wow, that's unequal sharing. There you've got more chocolate than I do. Well, atoms sometimes, lots of times, behave unequally in terms of their desire to have electrons near them. And that leads to a concept which you remember from previous courses called electronegativity, which some books write En, some books write the letter chi. I think our book uses both, depending what part you look at it. And electronegativity is a measure of the desire for an atom in a molecule to have electrons close to it. Okay, so it turns out that the fluorine atom has the highest value in the Pauling electronegativity scale, 4.0. Back in the day when I was at McMaster, we made a electronegativity scale, but it didn't catch on, and that happens sometimes. Pauling had already won 2 Nobel Prizes, so it's hard to compete with that guy. So fluorine is 4.0. That's the electronegativity. The next highest electronegativity is oxygen, which is 3.5, and it goes down as you run away from fluorine, both horizontally and vertically, and therefore also diagonally. We don't have data for noble gas electronegativities, really, and they don't form that many molecules. So for electronegativity, we stop at the halogens. And the more electronegative atom is going to get the partial negative end of the bond. So this lowercase Greek letter delta, that stands for partial. We aren't transferring a complete electron, we're just transferring part of an electron, and that's allowed in the magical world of covalent bonding. And your molecular dipole always points from the partial positive end in the bond to the partial negative. That doesn't always mean to left to right. I could draw this the other way, just and put the H here and the F on the left, but you always draw the arrow from the partial positive end to the partial negative end in the molecule. Okay. So this is unsymmetrical sharing. Okay, let me scroll down here. Yeah, we said all of that, didn't we? Okay. So any covalent bond between atoms of different elements is polar to some extent because each element has a different effective nuclear charge. Oh, good. The book's using chi. Greek letter chi. It's a funny looking italicized capital X, isn't it? So when two elements have different electronegativity values, a bond between their atoms is polar, and the greater the difference, the more polar the bond. So as the absolute value of the electronegativity difference increases, polarity increases, and sometimes this is called percent, or another term that is sometimes used, percent ionic character increases. So you have these electronegativity values, you take the differences in them, and the greater the difference, the more polar the bond is, the more unequal the sharing is, the more it's becoming like an ionic bond, till eventually you just grab the whole Kit Kat from me and then it becomes an ionic bond. Okay? It's related to but distinct from ionization energy and electron affinity, because those ionization energy measures how strongly an atom attracts one of its own electrons. Electron affinity talks about how strongly an atom attracts a free electron, but in electronegativity we're looking at a combination, we're looking at a molecule. And there's no units associated with electronegativity, it's a relative scale. Cesium has the lowest value, 0.7. Fluorine has the highest, 4. Here's a beautiful drawing of electronegativities to 1 decimal place. Again, these are average values, and for example, they'll say, oh, nitrogen and chlorine, they're tied. Well, in most cases, chlorine's actually a little more electronegative than nitrogen. And hydrogen, oh, it's much different than carbon. Well, in most cases, especially with organic molecules, we think of these as almost being the same as each other, and we say that the CH bonds in most organic molecules is really non-polar, even though there is a slight difference between them. But here you see fluorine is 4, francium is 0.7, so the greatest possible electronegativity difference you could ever get would be 3.3, right? We don't really deal much with the electronegativity numbers for the transition metals. Most of the covalent bonding we'll be looking at will be this non-metal region here. I could have talked more about transition metals with ionic bonding if I wanted to, but the focus here is on electronegativity and sharing electrons unequally in this region here, or non-metal region. Okay. We talked about that. So when you go to a limit like here, 3.3, it's an ionic compound. Cesium fluoride, 4 minus 0.7, 3.3. Whereas in the fluorine atoms, the change in electronegativity would be 0, so it's equal sharing. Hydrogen fluoride, so fluorine's 4, hydrogen's 2.1, so 1.9 falls in the extremes between pure non-polar covalent bonds and ionic bonds, and they're called polar covalent bonds. Then this part I don't want to emphasize, I'll just say it once. We often refer to bonds with delta chi 0.5 or less to be covalent. I don't even want to say that. Greater than 0.5 and less than 1.7 is polar covalent. I would just say if the difference is more than 0, then it's polar covalent. And 1.7 seems to be a borderline between polar covalent and ionic. But again, that's just a rough idea about that. So example 6.2 here, which is on page 260. Use the periodic table without looking up the values, just rank sets from least polar to more polar. So here you're looking for differences, right? So the greater the difference, the more polar it's going to be. So S and Cl, well, they're pretty close to each other. So that is going to be the least polar, okay? SeCl and TeCl, well, TeCl is the greater difference, so that's going to be the most polar, and SeCl is going to be between the two. And if you want, go back and use the numbers and get the differences. So the greatest difference will be between the tellurium and the chlorine. Tellurium is starting to get to be a metalloid, isn't it? Some properties of metals and some properties of nonmetals. The next one we got CS, CO, and CF. Okay, CS Well, that's in a different row. Sulfur is less electronegative than oxygen, so CS is going to be the greatest difference. Well, let's see. Let's look at some other things here. Greatest difference. So why do they have CS there? Let's go up here. Least polar, really? Let's see. Fluorine's the most polar. I agree on that, because that's the greatest distance from C to F. Then oxygen is the next highest polarity, so CO would be a least polar. CF difference. Well, there, fluorine is 4, carbon is 2.5, so the difference is 1.5. Oxygen is 3.5 and 2.5, so that difference is 1. Sulfur is around 2.6 and carbon is around 2.4, so that difference is just 0.2. So there the numbers did help. So the CS bond has the smallest electronegativity difference. The CF bond has the greatest. I guess we would figure that out. If we know that fluorine is the, I like to say fluorine is the king and oxygen is the queen of electronegativity. We won't talk about aces of electronegativity. Then the CS would have to be the least polar of them. Okay? Then you can try those practice problems 6.9 to 6.14. So to get the Lewis structures, and I'll just do a little bit of this and then we'll get into the more detailed ones next time, but we have a Lewis structure, just shows which atoms are bonded to which other ones and tells you the distribution of bonding and non-bonding valence electrons. We don't put in inner shell electrons, it's just the bonding and non-bonding valence electrons, named for a guy G.N. Lewis, who worked at Berkeley. Okay, I've never been there, but it'd be cool one day. So the conventions, and you've done these since grade 10, you use the elemental symbols to represent the atoms, but you only put the valence electrons. Line represent bonds. One line is 2 dots, double bond is 4 dots, triple bond is 6 dots, and then you have dots representing the non-bonding electrons. Okay, and so that is what that's all about. And these conventions divide molecular electrons into 3 groups. Core electrons are purely atomic nature, don't appear in Lewis structures. Fine. So basically your atomic symbol gobbles up all the core electrons. So you just put in the bonding valence electrons and you eventually put them as lines, or the non-bonding, and you put them as dots. Just as an aside here, when you're doing Lewis diagram just for an atom all by itself, there's hydrogen, there's fluorine, right? So this is an isolated neutral atom all by itself. Bonding framework, I also call that the skeleton. I like to call it the skeleton or the bare bones of what's going on. If you want to call it the bonding framework, go ahead. It shows all the atoms connected as they are. There's no foolproof method for putting them together, but there are some guidelines that'll help to put them together. An outer atom bonds to only one other atom, and an inner atom bonds to more. And you can have lots of outer atoms and lots of inner atoms. Here's glycine, which is an amino acid. So you have the hydrogens are outer atoms, and this one oxygen double bonded to a carbon is an outer atom. Then you have this oxygen, an inner one, and these 2 carbons, and whatever the heck that is, a nitrogen. Yeah, those are inner atoms. Hydrogen are always outer atoms. Another way to say outer atoms is terminal, meaning they're at the ends of the molecules. So hydrogens are terminal, and hydrogens are always going to be single bonds. Okay? In our examples, and halogens are usually also outer atoms, and halogens, right, the group 7A, are usually also just single bonds. Okay? If we have inorganic compounds, other outer atoms other than hydrogen usually are the ones with the highest electronegativities. So the least electronegative atoms are going to go in the central parts of the molecule. So sulfur dioxide has 2 outer oxygen atoms bonded to the inner sulfur atom. Silicon tetrachloride contains an inner silicon bounded to 4 other chlorines. Chlorine trifluoride has the chlorines inner because its electronegativity is less than the fluorines. Okay, I should say the atoms that are bonded to the central atom, there's a funny name for these. They're called ligands, like ligaments. So the atoms bonded to the central atom are called ligands. So in silicon tetrachloride here, right? Remember our naming system. Silicon tetrachloride. We're going to have a central silicon atom, and then you can have 4 ligands, each one being a chlorine ligand. Or chlorine trifluoride. Chlorine is going to be a central atom, and then you're going to have fluorines around the chlorine. Okay? This is what I'm drawing here are what I have here. The colored part here is called ball and stick models, which show you the molecular geometry, which we're going to get into later in this chapter. But the Lewis diagram doesn't directly give you the molecular geometry. This here is just the framework for getting the Lewis diagram. And then once you get the Lewis diagram, then you can start counting bonding pairs, lone pairs, and invoke VSEPR, which some of you looked at last year, valence shell electron pair repulsion theory. Okay. Okay, I just talked about that. Point 4. Atoms, the order in which atoms appear often indicate the bonding pattern, but not necessarily. So HCN often, well, carbon likes to be in the center of things, so that's good. So OCN minus likes to be in the center of things. By the way, you can get molecular Lewis diagrams for molecular ions, cations, anions, that's allowed. Molecular anions, molecular cations. This one, OCN minus, would be a molecular anion. CH3N2, right? So you have a framework here, you have a methyl group, and then you have a amine group to give you methanamine or methylamine. So this is a semi-condensed structure. Well, it is a condensed structure. Well, is that semi-condensed or condensed? It's condensed enough to show you that you have a methyl group and an NH2 group, and the hydrogens are grouped with the carbon and grouped with the hydrogen. Here on the left is a oxyacid. Oxyacids like to have a non-metal in the center and then oxy, so there better be oxygen in it. The oxygens do their best to surround that other non-metal in the central atom, and it's an acid. Acids like to hook onto oxygens. It doesn't matter which of the oxygens they hook onto, but once you have them here hooked on, then the other one is going to be different than those three. I'm going to talk about which ones you put on and averages and resonance structures. That's coming up a little later in this exciting chapter. So in the formula of an oxyacid like H2SO4 or H3PO4, hydrogens appear first, but they are still hooked to the oxygens, not to the central atom. Okay, so the hydrogens are not directly bonded to the phosphorus. There is some slight exceptions we can get to. So these 5 guidelines allow us to figure out the frameworks of many compounds, and then we get into building Lewis structures. So now we have those frameworks, so we'll take a breather, and then our next class we'll start building them. Let's just take a quick peek and see if our slides give any other details that help. Or covalent bond, there was those graphs. Bond energy to break the bond, strength of the bond length, we talked about that. Fluorine, we can get the overlap. Okay, non-bonding and bonding overlap, unequal electron sharing. There we have delta, electronegativity. Okay, it's not a bad idea to look at these notes if you want things in a quick, shorter form, concise. Okay, there's the question, Lewis structures. They get to the octet rule, but that's getting to our next class. Okay, have fun.